Imagine you are building a bridge across a canyon from both sides at once. You use the best instruments on Earth. You measure, remeasure, and verify every step. And when the two halves finally meet in the middle, they miss by 10 feet. In engineering, that means someone made a mistake. In cosmology, it is happening with the number that sets the scale of the entire universe, the present-day expansion rate. Two of the best methods we have give two answers that should agree, and they do not. This mismatch is called the Hubble tension, and if it survives the next wave of cross-checks, it is not a minor technical dispute. It is a sign that our standard picture of the universe is missing something real. The key quantity is the Hubble constant, pronounced h0. It tells you how fast the universe expands today as a function of distance. It is not a single speed. It is speed added per distance. The farther away something is, the more expansion adds to its recession speed. You will often see h0 published in the standard unit used in cosmology, kilometers per second per megaparsec. The two headline values at the center of the tension are about 73 and about 67.4 in those units. 1 megaparsec is about 3.26 million light-years. Over that distance, the higher value means expansion adds about 163,000 miles per hour of recession speed. The lower value means about 151,000 miles per hour over the same 3.26 million light-years. If you want an even simpler mental picture, divide that distance up. The higher value is roughly 50,000 miles per hour of added recession speed per 1 million light-years. The lower value is roughly 46,000 miles per hour per 1 million light-years. That is the whole idea of h0. It is a slope. Double the distance, double the added speed. So why do we have two slopes? Because we have two very different ways to measure it. The first way measures the universe now, from the present day outward. It is called the cosmic distance ladder. It is a ladder because it is a chain of calibrations. It starts with pure geometry, parallax. As Earth moves around the sun, nearby stars appear to shift slightly against the distant background. That shift gives a direct distance. Then you calibrate objects that act like standard light bulbs in space, objects whose true brightness can be inferred. If you know how bright something really is, its apparent dimness tells you how far away it is. A primary class of these standard candles is Cepheid variable stars, Cepheids pulse. The time between their pulses is tightly linked to their true luminosity. Measure the rhythm, and you know the bulb's wattage. Cepheids can be seen in nearby galaxies, not across the whole universe, but far enough to calibrate the next rung. That next rung is Type 1a supernovae. These are thermonuclear explosions of white dwarf stars. After careful standardization, their peak brightness is remarkably consistent. They are so bright that you can see them across vast distances, deep into the smooth cosmic expansion where local gravitational motions average out. So the ladder is built like this. Use geometric distances to calibrate Cepheids. Use Cepheids to calibrate the true brightness of Type 1a supernovae in galaxies that hosted them. Use those supernovae as bright markers out into the Hubble flow. Then measure distances and recession speeds, fit the slope, and read off h0. When this ladder is built with Cepheids and supernovae, it lands near the higher slope. It is the version where expansion adds about 163,000 miles per hour per 3.26 million light-years. That is one side of the bridge. The second approach does something completely different. It looks backward, not outward. It uses the oldest light we can observe, the cosmic microwave background, the CMB. This is the afterglow of the hot early universe, released when the cosmos cooled enough for atoms to form and for light to travel freely, about 380,000 years after the Big Bang. The CMB is a snapshot of tiny temperature variations, and those variations contain an enormous amount of information about early universe physics. They encode the densities of matter, the geometry of space, and the imprint of sound waves in the early plasma. To turn that snapshot into a prediction for today, you need a model. The standard model of cosmology is called lambda CDM. Lambda stands for a cosmological constant, the simplest form of dark energy. CDM stands for cold dark matter. Under this model, the CMB does not directly hand you today's expansion rate. It constrains early universe parameters, and the model then evolves the universe forward and yields a present-day h0. When the Planck satellite measured the CMB with extreme precision, the best fit under lambda CDM lands near the lower slope. In the terms we are using, it is the version where expansion adds about 151,000 miles per hour per 3.26 million light-years. Now you can see the gap. About 163,000 versus about 151,000 measured over the same cosmic yardstick. That difference is about 9%. And because the uncertainties on both sides have become small, the discrepancy is often described as being around the 5 sigma level. In plain English, it is very unlikely to be random chance. These two results do not comfortably overlap. For years, many people hoped the answer was boring, a hidden systematic error in the distance ladder. The most popular suspect was crowding. Cepheids often live in busy regions of galaxies. If your telescope cannot perfectly separate the Cepheid from nearby stars, extra light leaks into the measurement. That makes the Cepheid look brighter than it really is. If it looks brighter, it looks closer. If it looks closer, the inferred expansion slope becomes steeper, and h0 comes out higher. So the argument was simple. Maybe the latter is being fooled. Then the James Webb Space Telescope entered the story. Webb's sharper infrared vision can separate stars in crowded fields far better than Hubble can at key wavelengths. That makes it a powerful tool for stress testing the crowding explanation. Here is the critical point. Webb did not replace the entire distance ladder with a brand new, fully independent measurement and declare a final winner. What Webb has done is test whether unrecognized crowding in Cepheid measurements, especially a bias that grows with distance, could explain the tension. And Webb's results strongly reject that specific explanation. In other words, the simplest story where the ladder is high because Hubble blurred Cepheids into looking too bright, in a distance-dependent way, does not solve this. So where does that leave us? It leaves 3 broad possibilities. First, the distance ladder still has a bias, but it is subtler than the obvious crowding story. It could involve how Cepheid brightness depends on chemical composition. It could involve dust corrections that shift slightly with environment. It could involve how supernova brightness is standardized, and whether there are small population differences between host galaxies. These are real astrophysical effects that must be modeled. The reason they matter is that the ladder is a chain. A small bias at one rung can propagate into the final slope. Second, the early universe inference is off because lambda CDM is incomplete. Planck's CMB measurement is exceptionally precise, but the translation from that measurement to h0 is model dependent. If the model is missing a real ingredient, the inferred h0 can shift. A major class of ideas here is early dark energy. The concept is that a temporary additional energy component existed in the early universe for a short time, changing the size of the standard ruler imprinted in the CMB. If the standard ruler is smaller than assumed, you can infer a higher h0 while still fitting much of the CMB structure. This idea is attractive because it targets the exact link between early physics and late expansion. It is also hard to make work because any change you make to the early expansion history tends to affect multiple observables at once, including the detailed pattern of the CMB and the growth of cosmic structure. Other proposals involve extra radiation, changes in neutrino behavior, or interactions within the dark sector. The pattern is similar. You try to move one number, and the rest of the universe immediately checks your work. Third, the region we live in might not be perfectly representative. If our local cosmic neighborhood were underdense on very large scales, it could make local expansion appear slightly faster. This is the local void idea. The problem is scale. To move h0 enough, you need a void that is large and deep enough to clash with other maps of large-scale structure. And as local measurements extend farther out, it becomes harder for a local feature to explain a persistent offset. Now add one more reality check that matters. Not every late universe method lands at the high slope. There are alternative calibrations of the distance ladder that use a different anchor called the tip of the red giant branch, the TRGB. Many TRGB-based analyses land closer to an intermediate value, roughly between the two extremes. There are also intermediate and consistency probes, like baryon acoustic oscillations combined with other datasets, that often prefer values in the high 60s in the usual units under common assumptions. So the honest situation is not a cartoon with one clean number on each side and one telescope declaring a victor. The honest situation is that the two anchor approaches remain in tension. A major, simple, systematic explanation has been weakened by Webb, and other probes populate the middle, each with its own assumptions and limitations. That is exactly what an unsolved scientific problem looks like when it becomes mature. It becomes hard to dismiss and hard to solve. So what is actually at stake? If the lower slope is right, then the standard model remains self-consistent, and the main work is to find the subtle bias in the local ladder. If the higher slope is right, then within the standard framework, the entire web of parameters becomes harder to satisfy without changing something fundamental. That does not automatically mean the whole model is wrong. It means something in the blueprint is missing. And either way, H0 is not isolated. It is tied to the sound horizon scale from the early universe. It is tied to matter density. It is tied to how structures grow. It is tied to gravitational lensing. It is tied to the calibration of cosmic distances across astronomy. That is why this number matters. It is not just a slope. It is a stress test on the entire cosmic story. So what happens next is not one dramatic announcement. It is convergence. More Webb observations that expand Cepheid tests across more supernova host galaxies. More supernova datasets and calibration cross-checks. More geometric anchors. More strong lensing time delay measurements that provide an independent late time route, limited by how well we can model the mass in lens galaxies. More large surveys mapping the universe in 3 dimensions, testing expansion and structure growth together. Here is the key idea. If the tension is caused by hidden systematics, different methods will drift in different directions, and the pattern will expose the culprit. If the tension is caused by new physics, the universe will not hide it in a single measurement. It will show up as a consistent shift across multiple independent probes once the data become tight enough. That is why the Hubble tension is not a failure of science. It is science at its most honest. It is what happens when measurements get so good that the universe can no longer be forced to agree with our expectations. 2 halves of a cosmic bridge built with our best tools, meeting in the middle, and still not lining up. If the gap holds, the conclusion is not that we know nothing. The conclusion is sharper. Either the local cosmic distance ladder has a subtle bias we have not pinned down yet, or the early universe blueprint is incomplete, or both. And inside that gap is either the hidden error that will make our measurements stronger, or the first clear sign of new physics in the expansion history of the universe. The universe is still expanding. The real question is whether our model of why it expands the way it does is complete. Right now, the Hubble tension is the loudest sign that the answer might be no.